I want to talk today a bit about RMOD. So I guess that you have seen mostly in the context of Faro or maybe Moose this strange name. And I think it's a bit not really well known what is behind it, and so I want to explain a bit the structure, and especially I want to explain the overall research topic and how the things that we do fit into that. So RMOD is a research group at INRIA in Lille, and INRIA is a government research lab in France with a structure that it has lots of research project teams that are relatively independent and do research in one direction or in one topic. And RMOD is our team, and as a typical INRIA project, it's actually a shared project between INRIA on one side with Stefan and myself and the university, or the university in Lille, in this case an engineering school. And so in our group we have INRIA people, but we have two professors from the university too. And in addition to that, the typical setup that you would find at any university. So from that point of view, it's kind of no real difference to coming into a university. We are even sitting at the university itself, so in the normal university computer science building. So we are the full-term or long-term employees, and then we have right now 2 engineers, 1 postdoc and 3 PhDs. And this engineer thing is kind of one thing that makes us different from a normal university. So if you look at the university, at least in Europe, it is nearly impossible to hire a programmer. So there is no money for that. You cannot do that. So in the end, you need to do everything that you want to do in software development. You need to do either yourself as a professor, or you need to kind of bring your PhD and master students to do development, which is always a bit difficult because the goal of a PhD student is not to do software development, but to get a PhD. There is really a clash normally between doing something that is long-term for even after the PhD is finished and something that is just for the PhD. And so we are now in the nice setup that we can actually have programmers in addition to the researchers and the PhD students. And in addition to local people in Lille, we are extensively collaborating. So we have another engineering school close to Lille in a small town 30 minutes away. So for Argentinian sizes, that is inside the city, I guess. So, and then we have 2 PhD students, one of is Mariano that we all know, I guess. Then we have a PhD student in combination with the University of Brussels in Belgium, which is not far away either, so this takes 35 minutes by train to go there. So close. And to counter that a bit, we have 1 postdoc in combination with Chile. And he is actually sitting in Chile, which is a bit modest. And the question is, what is the overall research direction that we have? Because there's a lot of stuff happening. How does that fit together? And the overall theme of RMOD is that of software evolution. And I want to explain a bit of what that means. So if you look at software, then historically people were thinking that the real difficult thing is to develop software until you can release it. So, because then you have it and it's done. So you develop, put a lot of effort into it, you do beta tests and testing, and then you release, and then you think it's done. I only need to maybe do some bug fixing, but you know, this is clearly where the money is spent. And according to this model, all programming languages are designed. So programming languages are meant to be used to build something and then it's done. But if you look at it in reality, so if you look at what happened over the last 40 years, then it looks completely different, because development of the first version that you give to the customer is from the overall amount of money that you spend or the effort that you spend is maybe this, and the rest is here in the maintenance. So developing is actually not a problem, because you are doing it, you have no customers, you can change everything, you're free. The fun starts when it's at the hand of your customer. Then changing something is really difficult because people complain, or you cannot change it because they need it. And then the software really complicated and you want to change something, it's really difficult, then it might be that people that did this, they leave the company here, or in the case of whole projects, it's really the case that they retire at some point. So the people that actually did this effort are not available to do that, but because this one is far longer time period than the development. So in general, we can actually say that contrary to what people are always thinking when they start a project, software lives forever. So even when you now start something and you're 100% sure, we use it just once and in 3 years we have the second version done, that replaces it completely. It will not happen. So everything you do will live on forever. I think if you, so taking that into account, it will be far often more right than if you say it's a throwaway project and it will be replaced. So in a way, you can actually say that what we have are eternal systems, systems that live forever. There is no stop point. And there is no point where you replace the system by re-implementing it. So in the past, when Java came along, for example, there was a huge kind of effort in many small projects where they said, we will just replace the small project. We will just rewrite it. That's easy. New language, much better, much more programmers can program it, much better tools. So we will just rewrite it. And in the end, it's amazing that how many of those projects did actually not succeed. Because you have something that works, as opposed to something that does not work. And often then, the thing that works will win, even so it might not be perfect, and there are many things that you can improve. So, in the end, it means that it's much easier or better to embrace evolution and to say, yes, we know it will live on forever, so instead of planning to rewrite it, to just accept that you will actually improve this system and not some hypothetical system that you will start to develop on in the future. And that is our research overall theme in the end, to ask if that is the effect that software evolution is really important and that it will happen anyway, that you will have to maintain something forever, or that you will have to move your crappy system towards the next step instead of rewriting it, then what actually can we do to help the programmer to do this easier? I mean, if it's real, it will happen, so we need to make it easier. And the first thing that you directly realize is I need to be able to evolve my applications better. So I have an application, million lines of code written in COBOL. All the people that developed it are in retirement. What do I do? And so there are things that are clearly relatively clear in which direction you can go here. So one thing is that knowing about the history of your code is always interesting, so that you know what the people in the past on this system, so that you can understand more why it looks like it looks like. Or program understanding in general, so you have a huge system and where do I start? No idea. Or a field on its own which kind of helps program understanding and software visualization in general. So how can I understand the system without reading all the source code? So what people from this field always say, imagine you have 1 million lines of code. You cannot read that because it will take too long. It's impossible. And at some point we will be in the future in systems that cannot be read anymore because they are just too large. So the idea of software visualization is to actually take the source code and visualize it graphically, abstract it away from the text. So to have bigger structures and to show so that you can actually understand how components fit together, or where can I improve something more easily. The second step, so I mean, this is clear. We have already software building tools that is will clearly help software building. Another question, and that is far more, it's a bit newer and a bit more difficult to understand, to accept. All the languages that we use today are not designed with evolution in mind. So languages are made for a program, I ship, and that's it. And the question is, can we improve the language itself to support software evolution? So to really think about language features, to really put it down into the system itself. analyze and help, but to really change the language to make it easier to evolve. This is, for one, it fits very nicely in the overall topic, but it is kind of politically nice too, because a lot of topics from language research fit into that. So if you can directly, if you have this in your program of research, you can directly work on modularity, because a more modular system is one that evolves easier. Or you can work on reflection, because reflection is about evolving at runtime, or support for tools to analyze them. And so in the end, a lot of the topics of language engineering or language research fit into this. You can even completely do something which has nothing to do with evolution. For example, if you say, I want to have a cloud smalltalk. Clearly not about evolution, but what there is about evolution is the question, how can I evolve my current system into a cloud smalltalk system? And then you're again in this topic. So it's really nice from this point of view. I mean, you can have it as your research topic and you can work on it forever, because it's very flexible and very relevant at the same time. And the next step, after thinking about improving the language to support evolution, is the question of how can I improve my language so that it can actually evolve faster itself. Because if I start to change language, then I evolve the language. So if I improve modularity, for example, then I have the problem that I need to change my existing language to have this new modularity concept, and that might be really difficult. So the question is, can't we improve the language to make changes easier, so that we can actually implement our changes faster or nicer or without hurting other clients who kick back or competitors. And so the question here is, how can we evolve the language itself, and how can we change the language so that it evolves much easier, or that self-evolution gets easier. So in the end, you want to have a self-evolving system, so that it kind of allows you to construct its own future easily. And after this kind of more very high-level description of the overall topic, I want to actually show a bit examples of things that we are working on or that we worked on in the past that fit into this topic, so that you can see how this looks like in practice, and that you have a feeling of what we actually do at RMOD. So the first thing is evolving applications. So we have old systems, what do we do? And there, what was done over more than 10 years, I think, is the Moose platform. And Moose is a platform for software analysis and data analysis in general, which is implemented in Smalltalk, because Smalltalk is the best language, we think, to do this. Originally, it was done in VisualWorks, Smalltalk until 2008, and then Faro since 2008, and actually Moose was kind of a reason why Faro was, or one of the reasons why Faro was created, to be the basis of the system. Because VisualWorks, mostly license problems, it was really a challenge to use. So, for example, it was not allowed to have a download of Moose on the Moose project website. You were only allowed to have a link to the non-commercial VisualWorks and the description of how to load code. And this, of course, if you want to make something public in a way that you really try, this is impossible. And with Faro, the nice thing is that there is now a download. You download, click, runs, nice. And yeah, so with Moose, what's interesting is that it directly, or even so it was implemented for, or designed to be something about application evolution, it already has something about, or an implication for language evolution. So if you see, we build Moose on top of Faro, which in turn means that every improvements that we do here will directly be an improvement on Moose. And we have seen that in the last versions very nicely. So some of the changes that are actually were requested by the people of Moose, or even implemented by the people of Moose, and then integrated in Faro. But at the same time, as Moose is a visualization platform and analysis platform, we can actually use Moose to analyze Faro, to understand it better, to find problems, to structure it better, to evolve it, to So Moose as an evolution platform for Pharo. And this is now starting slowly. So after it was implemented on top of Pharo, now we start to be in a situation where we can actually do this in a very nice way. And so what you have in the end is a feedback loop between the re-engineering software visualization platform and the language itself. Very powerful, and I think this will drive a lot of the evolution forward over the next years of both systems, this feedback. But language support can mean something else too. I mean, not only using a tool on top of the language, but really changing the language for the better so that it provides direct support for software evolution. And one of these things that are easy to understand how this fits is the code model infrastructure that is now in Pharo model 4, the ring meta model. This is a slide from the talk of 2 days ago. So imagine you would have a meta model of code that even includes the history of the system. Then you can easily understand why things are like they are now. Because often in a system that really is a real world system and not a beautiful thing that was done by one person, but that evolves itself, you always wonder why it is like it is, because it's sometimes really not understandable, because who would do it like this? It's clearly strange. But if you then have the history, you can understand why people did it like this, because you see how it actually evolves from that point. Or if you start to really develop and you have 2 branches, so one PhD student did something and some person in the company did something, and then at some point they will want to sit together and make small talks or issue and merge the stuff together, then you need really good support for modeling the history so that you can actually merge it in a meaningful way. Or another direction of this is that you have actually the source code of the whole history not on your disk because it might be a bit large, but available on the net so that you can use it when you need it, but then it does not make the system more heavy. So this is the Ring project, and it's done by Veronica, and she is in Brussels actually, a PhD student. So this is the collaboration with Brussels. And another thing that is very interesting to think about and really difficult to solve actually is the what one could name the consistency problem. So imagine you build really large systems using your language. So you have one program which is really big. Then the problem is that a program with a programming language that is built with a programming language always needs to be consistent. So for example, in the sense that you have one library in one version in the whole system. So you have one HTML parser, for example. And if the system gets really large, then that means that you need to move all the points in your system that uses this one library towards the new version at the same time. And that might be really, really difficult. And if you look in the real world of big systems, how they exist in companies, then you see that it's often some kind of internet infrastructure, servers and services. And there, it's not the case. I mean, you have a web server here and a mail server there, and they do not need to update the Linux on both on the same time, or they are touched. There can be different versions without the problem. But programming languages do not allow that. I can only do that when I step out of the language, build an application, and put APIs between them using typical web technology. But the language itself does not allow me to build a system with different versions of libraries. It doesn't exist. So that is something that we clearly need to think about of what we can do, so that we can actually evolve parts of the system completely independently, or that we can do experiments in the system without having to make it real directly. We started to have one experiment in that direction, and that is called object spaces. And here the idea is that the starting point is that you say the smalltalk image is actually a quite cool idea. And why can't we do with the smalltalk image? Why can't we bring the smalltalk image as a concept into the language? So something that's, I mean, it's around the whole system, so it's not available in the language. The image is nothing. It's not an object. So why can't we put the image itself as an object into our language and provide multiple consoles so that you can actually say in a hypothetical Pharo 2.6 that you can say, please instantiate the Pharo 2.2. Make me a small image which is an object, and then it runs inside the same system in parallel to the rest. This would allow you to do things quite nicely, because 2.6 might be nice for developing, but my commercial project runs in 2.2 and has no commercial incentive to ever move to the new version because it runs fine. My client is happy. Why should I move to 2.6? But if I could run the old version in the new system, then I would be guaranteed that it would run on the new VM nicely, that I could maybe use the tools of 2.6 on my 2.2 code base, for example. So, quite nice. So, quite nice. And we think that this will actually bring a lot of open space for experiments. So, it's kind of a different form of modularization. Maybe it could provide something like that. Provides a bit of security because you have a sandbox in your system, maybe you could use it for that. That if you have a CISA application runs in this kind of sandbox and it crashes, it doesn't take a whole server visit. Distribution, concurrency are all things that could come out of this direction. Yeah, When was is working on these things in this direction. He's a PhD student in it. Another direction which is a bit similar, but it takes a completely different point of view, is the handles project. And here we do not build a box of the whole system, but instead we look at references in smalltalk. References are very interesting, but they are just references to objects. They are not objects themselves. And the question is, what happens if I make an object out of a reference and provide a way of changing the behavior of the object that I reference from this one reference, and maybe even a way of, if I change state, it keeps on only. So if I reference it from this reference, I see the state change, from the other one I see the original. Interesting research question, and one can do kind of nice things with it. So what we did already and published is read-only execution, so that you can really say to an object, give me a read-only reference, and then everything that I do from this reference, so if I send a message to it and this is a huge calculation involving many other objects, everything I do from this reference out will be read-only. That means as soon as I assign a value to an instance variable, it will raise an error. If I don't, it will just continue to execute. And this means that the system kind of looks different depending on if I use this reference or another reference. Another direction that we are looking into with this functionality is to build transaction support, because we think that this has all the features that you need to actually implement transactional change in whole object graphs. But this is a bit in an early stage of development or research. Another direction for languages is to improve evolution support in languages, is to look at embedded systems. So embedded systems historically are very static. So you do them in C, and then you deploy them, and when they're deployed, you have no way of doing anything. You need the serial console to do debugging, and the debugger is really bad. And it's really a strange world to be in. But over the last years, the resources actually that you have in the embedded system is much, much better. So you can actually now get embedded hardware that are in the size that you can run a normal smalltalk. I mean, even in German. So 32-bit ARM chips with hundreds of megabytes of RAM for cheap. Quite nice. And the question is, how can you, in a system like that, improve the development in embedded systems? And so one of the things that we do is that Mariano talked about this is the Maria project, where we say, yeah, we have more resources but not enough, so we need to actually think hard about resource management. So we need to move unused objects to a second storage if we have only not that much RAM. Or another direction is remote reflection. So the ability to reflect on the embedded system from my nice from on my desktop, which is an interesting idea. And the funny thing is that this directly has influence on the object space idea, because this functionality to reflect on a robot that is on the floor, you can directly use to reflect on an object space in your image itself, or an object space that is on another machine. So quite nice. This is all about improving improving evolution support in the language. The other question is now, how can we evolve languages themselves easier? So how can we improve the possibility of evolving languages? And here, there are some things that you can easily find that would improve it a lot. So yesterday I gave a presentation about work of Benjamin and Gwen, originally about the idea of bootstrapping smalltalk from nothing or from text. So you have an environment that's empty, and then you say, please make me a smalltalk from this description. And the idea here is that it improves evolution of languages because it allows you to change the description offline while it's dead. And then you say, please make me a language. And then you have a new language kernel running that might be completely different. So maybe no traits from the dead traits, or that it has traits differently, or that has multiple inheritance instead of single inheritance, or that has a coda style meta object protocol that we saw in show us the projects based on things like that. So to make it really easy to build new language kernels. And the last idea in this direction that I want to show is the idea of if we improve the language, then there is always this virtual machine that is there on this. Very difficult to change because it's just a binary piece of code. And there, I mean, the way we have is really good. Improve the practical use of Pharo a lot. I mean, especially one of the examples is Moose. I mean, Moose with the current just-in-time compiler is a completely different beast than it was before. It is really practically usable on big analysis. But on the other hand, it is a complex piece of code, and it's a static piece of code. It's a binary blob on disk, and you cannot do anything with it at runtime. And it's very hard to understand for students how to change it, difficult to use for researchers to do experiments. And so the question is, can't we improve that somehow? Can we make the VM evolve easier? We did some stuff that's really down to earth, like this Jenkins server that can compile directly a VM from source code, a VM. That already is something like that, because we had the problems that students were changing the VM for an experiment, and then when some other student came and wanted to look at it because his topic was similar or to do similar things, then this code was completely lost because it was stuck on someone's disks, and building it was really difficult, and nobody understood it. Doing it takes, I don't know, takes maybe a month to be able to build a VM from scratch, and then he has not changed anything until then. And so this pure engineering work was already done to enable us to have a student watch this video, then you can build a VM, put it into Git, and set up Jenkins like this, and then you have a full system that builds all the time, and then you can be sure that we don't lose the experiment later. Yes, so that was it. Does anyone have questions?
Is something I didn't quite get is Moose, the project that involves all this stuff that you've been.
No, Moose is just one of the projects. So the project that involves all of them is the research done on RMOD. Bit of all what happens in the team, and then there are artifacts, so real things that you can download, and one of them is Pharo, really, and one is Moose. And the idea is that we actually want to things that we do as research. Many of them will be just experiments, and they will be published about, and that's it. But some of them we want to then revisit with the help of the programmers that we can hire, and say, we did some research, it was a big hack, but it showed it was really cool, and I would like to have that, but in a way that is really stable and good. And then we can revisit it and say, I guess we put that in Pharo. So Pharo actually will, over the years, acquire all these features that we invent and research, or the ones that make sense in the real world. And this is happening now already. So the ring meta model is in 1.4 already, the first one. And we will see far more of this feedback into Pharo in the future.
I have a question.
Yeah.
You talk about language evolution.
Yeah.
Do you have some ideas about how smalltalk evolved as a language?
Yes. So one thing that I did not present at all is there was some work done in Bern about the idea of having first-class slots instead of instance variables. So they have objects describing instance variables, so that you can actually make subclasses of this class to make variables that have special semantics. So you can what they present in a paper. So that was presented at Booster this year. What they present as a Boolean slot, and the idea of a Boolean slot is that it can only have true and false, and if you assign something else, that raises an error. And in addition, over the whole hierarchy, the system will collect all Boolean slots for your object that you instantiate, and just put it into one small integer and use it for stuff to store all the Booleans in one small object. Or property slots that will allow you to declare a slot as property, and then it will, in a hidden way, have a dictionary in this object, and all property slots will be in that dictionary. And so you can make as many properties as you want with the slots, and they will take the same space if they are not used, for example. Which will be nice for Morphic, because Morphic has a huge machinery of has, I don't know, 4 instance variables in Morph, and then it has an extension with 8 more that are used a lot, and then 150 of properties that are in the property dictionary, and it's a huge mess. And if you would be able to put that into the class definition, then it would be much more understandable. So this is an example of something where we want to evolve the language, because this properties, they will support evolution because they make the system easier and more powerful. And it's a question of how do I evolve the system to do that without destroying everyone's use. Any more questions?